General Srivastav, ladies and gentlemen, a very good morning. It's indeed an honor to chair this session on advanced materials for aerospace, consisting of subject matter experts from the academia, the research institutes, and the industry. I'm thankful to the St. George and Indian Military Review for providing me this opportunity. In my opening remarks, for the next 7 to 8 minutes, I'll briefly cover the background of aerospace materials and also the important role of the needs of the military on not just developing technologies for new futuristic platforms and engines, but also in sustaining the variety of foreign assets that the services possess in its inventory. By sustenance, I imply the self-reliance initiatives that we need to undertake to keep this costly equipment available for warfighting. So aerospace materials have come a long way from cloth and wood to advanced superalloys, composites, and self-healing materials. The consideration of aerospace materials is crucial to the future of aerospace industry in general and military in particular, as engineers are constantly looking for ways to extract the maximum performance from the platform or the power plant during design as well as in the exploitation stage. World War II brought in rapid progress in aerospace design. Aluminium became the most popular material due to its lightweight and other characteristics, and of course, cheap and easy to produce. New, more complex materials were beginning to be used, such as titanium, graphite, fiberglass, and other composites and alloys. Today, the usage of pure aluminium is very little. But however, these alloys are used in the aluminium is also used in alloys which have high qualities, such as titanium and nickel-based alloys. These alloys make it possible for the production of high-performing parts and are able to withstand extremely high temperatures, pressures, and corrosion. These enhanced properties are a result of included elements such as these aluminium and chromium and other elements. Besides alloys, composites were also widely used in aerospace industry. They have less weight and thus better fuel efficiency while still being able to easily designed and manufactured. Carbon fiber reinforced polymers, which are fiber reinforced materials that uses carbon as a primary structural component, dominate the composite materials today. Composite materials will continue to be the key to making aircraft lighter, stronger, agile, and less expensive to build while cutting down fuel consumption and CO2 emissions. The evolution of aero engine manufacturing technologies, especially for turbine blades, is also as equally interesting as the aircraft materials. While the initial engine was made from aluminium, the materials graduated to stainless steel, cobalt, titanium, turbine coatings, powder metal superalloys, thermal barrier coatings, ceramic metal composites, and intermetallics. The processing technology also graduated from vacuum induction melting, arc melting, investment casting of complex shapes, multiple vacuum melting cycles, isothermal forging, large structural castings using electron beam and physical vapor deposition. Directionally solidified and single crystal blades, laser deposition, and silicon carbide melt infiltration are the buzzwords today. In the near future, heat resistant superalloys may be gradually replaced by ceramic metal matrix composites, which are on average 1/3 the weight of nickel-based superalloys and can withstand higher temperatures. An issue with composite materials is that they often require specialized methods of maintenance, as defects in the material are hard to detect and prevent the entire composite from performing properly. To account for this, self-healing technology is being researched and developed. One of the methods being studied is the use of liquid epoxy resin, a type of polymer, to reach the damaged area and repair it quickly by hardening. The implementation of self-healing materials will greatly reduce repair and maintenance costs of the aircraft and allow for greater possibilities. Futuristic material include metal matrix nanocomposites, known for their high tensile strength, electrical conductivity giving resistance to lightning strikes, and many more such properties. Polymer and ceramic-based versions of this material are used in carbon fiber reinforced polymer wings to protect against electromagnetic interference. Other future materials and technology include biomimetic material designs, graphene-based materials, advanced health composites, shape memory alloys, morphing aerofoils, and many more. As in the past, researchers continue to develop the new materials to be used for aerospace applications. Defense research and development is not just building the military power of a state and strengthening the strategic independence, but also a major factor providing a positive impact both on the development of scientific and technological progress. The contribution of DARPA, the Defense Advanced Research Projects, is a much quoted example. In India too, the need for high performing platforms, power plants and systems for defense and aerospace applications are spawning research in many areas. Today, we have esteemed panelists who will be talking about some of the cutting-edge technologies which have been associated with. While we look forward to these presentations on cutting-edge technologies, I would like to flag seemingly mundane yet important issue which services in general and Indian Air Force in particular are facing. There are immense challenges in sustaining foreign technology and equipment, overcoming supply chain challenges, and ensuring availability of our combat assets in an era of geopolitical upheavals. While cutting-edge research and innovations are a must, at the same time, converting a collective knowledge to areas requiring urgent intervention is required, as it is a matter of sustaining our combat readiness and national security. Here, I would like to focus on two key areas. Firstly, indigenization of materials and parts, which would need considerable lead time before we achieve some degree of self-reliance, and therefore the need to buy time till our homegrown innovations and research lead to indigenous world-class systems. Buying time through life extension projects by extending preventive maintenance periodicity as well as total technical life of the platform or the system. I would like to take the example of the sustenance of aero engines as an illustration of the urgency to indigenize materials and parts. Dependence on inputs limit our indigenization efforts. Today, the country has not achieved self-reliance in the sphere of jet engine manufacturing. We are dependent on foreign OEMs to transfer technologies, supply material, and semi-knockdown kits. Sustaining availability of engines for our fighter fleets is a huge challenge. Though significant progress has been achieved by organizations like Midani in developing alloys for strategic applications, the nation faces four main challenges. Firstly, availability of raw material, for which considerable efforts have already been made to establish sources and stockpiling. The National Mineral Policy of 2019, the 30 key minerals identified this year, the Rare Earth and Energy Critical Elements Roadmap for Strategy for India 2012, and the impending National Material Policy are steps in the right direction. However, these initiatives need to be quickly implemented on the ground for reaping the benefits. A strategic metal bank is the need of the hour, and it is in the interest of the country to carefully craft an appropriate strategy to realize this objective. In fact, leading countries have already taken significant steps towards this aspect. The second challenge is overcoming the MOQ problem, the minimum order quantity. The quantities needed can only be brought closer to this MOQ if aggregation of all the requirements is done across services, all sectors, and even civilian applications. The requirement of different varieties of alloys, forms, shapes needs to be rationalized. For example, if I take the Su-30 aero engine example, 1385 forms and shapes are required to manufacture the engine. Now, they are of various quantities, various varieties. If we can rationalize the type of rounds, the size of rounds, the size of hex bars, or the material required, you can build up the MOQs. And it will be much more easier for Midani or any other industry to manufacture them. The third challenge is the availability of technology to realize the requirements. Towards this, DMRL and other institutions have been researching and developing various alloys, and the same needs to be facilitated. The GE HAL deal for the GE 414 engines is expected to bring in 80% technology transfer. It is likely to bring in technologies like special coatings for corrosion, casting, machining, and coating for single crystal turbine blades, nozzle guide vanes, other hot parts, blisk machining, forging and powder metallurgy discs for turbines, machining of thin-walled titanium casing, friction inertia welding for fan and afterburner, polymer metal matrix composites, ceramic matrix composites for LP nozzle guide vanes, and so on. The fourth main challenge is the constraints in the availability of necessary facilities for processing and manufacturing these materials. For example, as the Secretary had brought out this morning, non-availability of a high-capacity press, for example, a 20,000 ton or a 30,000 ton press, is limiting India to manufacture turbine discs. Life extension studies will buy us time to indigenize as well as mitigate the supply chain constraints and compensate for delays in support from the foreign OEMs for repair and overhaul. By life extension, I mean extending the total technical life of the engine or the aircraft by doing scientific studies. While organizations like CSIR, NAL, DMRL, GTRE, and CEMILAC are geared up, we need to develop tools to analyze how performance of materials degrade over a period of time. Setting up facilities like the spin rig test enables us to do residual life analysis. These areas of study not only help in taking life extension decisions, but also enable better understanding of the design, materials, and the system engineering aspects. In conclusion, the need of the hour is to create the right ecosystem, strategize raw material requirements, create incentives to pursue self-reliance in strategic material, R&D, processing, and manufacturing. The time is ripe to harness our collective wisdom and knowledge gainfully to be a self-reliant Atmanirbhar Bharat. I would like the think tanks to consider championing the cause for a national mission of self-reliance in aerospace to orchestrate a revolution in this field through effective strategizing, policy making, coordination, and mission mode implementation. Jai Hind.